All right, General Chemistry Tribe, we are now looking at examples. And we're looking at an example of now using Gibbs free energy equation. And our example looks at basically a reaction that titanium tetrachloride can be produced by the reaction of tellurite or titanium dioxide and chlorine gas. And so we can write that reaction as such, that we have the tellurite or the titanium dioxide reacting with two chlorine molecules to produce titanium tetrachloride and then oxygen gas. This is actually a redox reaction, but one that we will classify much later in subsequent lectures. So what we want to do is we want to calculate the delta G for the reaction, and is this reaction spontaneous or not? If it is not spontaneous, is it temperature dependent? And if temperature dependent, at what temperature will it be spontaneous? So really a bunch of questions there. We have the reaction as far as the tellurite and the chlorine gas making titanium tetrachloride or standard chloride and oxygen gas. We need to calculate the delta G and then answer these other questions. So we have a number of multiple parts to this, meaning that part A would really involve calculating delta G of the reaction. Depending on the sign, we have this notion of whether the reaction is spontaneous or not. So that would be really looking at part B. Once we've calculated delta G, what is that sign? And then the next bit, part C, is it temperature dependent? And that's going back to this idea of driving force. Are both things driving forces, or is only one driving force? Or are none of the ideas of delta H and delta S the driving forces? So that's our temperature dependence. And then if temperature dependent, what temperature will make it spontaneous? And so that might be part then D. As far as, okay, now let's calculate a temperature at which we're at the cusp, and now we can move from something that's non-spontaneous to something that actually is spontaneous. So, in looking at part A, we're asked for the delta G of the reaction. And our delta G for the reaction from our Gibbs free energy expression is equal to delta H of the reaction, or the enthalpy of the reaction, minus our temperature times the delta S, or the entropy of the reaction. So we basically have to go to tables and substitute proper values of delta H and delta S. Since there is no mention of temperature in the question, you want to assume 25 degrees Celsius or 298 Kelvin, which is that standard state idea, and that's why we have those superscript zeros with all of those terms, delta G, delta H, and delta S. So let's start with our delta H. This is going back to old topics in the first part of general chemistry, where we have to look up the enthalpies of our products and our starting materials, and sum them up with how many of them are made, or how many of them are turned over into product, as well as those energy values. So in looking at our delta H of reaction, we would look at this in terms of, okay, what are our products? Well, we have the enthalpy of the titanium tetrachloride, and that's a liquid. We then have our oxygen as well. And then that's going to be minus our starting materials. So we would be looking at the enthalpy of titanium dioxide, and then that would be minus basically 2 times the enthalpy for the chlorine gas. So those are our enthalpies that we need to plug into the expression. We have our products On the left side of the equation, we have our starting materials on the right. So here's where we need to go to tables and actually plug in these actual values. So our enthalpy of reaction, our enthalpy for the formation of titanium tetrachloride is a negative 804 kilojoules per mole. And I apologize for that expression above. We should have plus signs in those brackets, which I'm correcting right now. Right? Because we want to take the sum of the products minus then the sum of the starting materials. So we should have addition signs within those brackets. So we have a negative 804 kilojoules per mole for the titanium tetrachloride. And oxygen, since it's actually elemental, would be 0. And then that's minus the enthalpy that we would have for our titanium dioxide, which is a negative 944 kilojoules per mole, plus 2 times then the enthalpy for chlorine gas. Again, chlorine gas is how chlorine exists in nature, so that would be as well a 0 kilojoules per mole. And we can look these values up. As far as looking up these values in the tables. So our delta H of the reaction is actually equal to that negative 804 kilojoules per mole minus a negative 944 kilojoules per mole. Or our delta H of the reaction, once we do that quick sign change, is equal to 140 kilojoules per mole. So if we look at that enthalpy aspect, the fact that it's positive, this is basically not a driving force. So that's our first bit to answering the question of delta G. We have the delta H portion of that equation. So now we go to the delta S portion of the equation. And it's very similar to what we see above for our enthalpies. We see the same thing for our entropies. That we're just looking at a sum of the entropy of our products minus the sum of the entropy of our starting materials. So we would look at, the entropy for our titanium tetrachloride product plus the entropy for our oxygen gas. And so there are our products. And then we would subtract that from the sum of our entropy of our starting materials, namely the titanium dioxide, plus 2 times the entropy of the chlorine gas. Now, while enthalpy with elements as they exist in nature are 0, remember that with entropy, that there is no 0 value. So all of these molecules have an actual entropic value. So we go to tables to basically look these up again. If we look at the enthalpy of our oxygen gas, we have, of our titanium tetrachloride, we have 205 joules per mole Kelvin, plus the entropy of our oxygen gas, which is 252. So there are our products. The entropy of the solid titanium oxide is 50. Joules per mole Kelvin, plus 2 times then the entropy for the chlorine gas, which is 223 joules per mole Kelvin. So if we sum that all up, we end up with a delta S of reaction to be equal to negative 39 joules per mole Kelvin. And if we look at the sign of that, we see a negative delta S of reaction, and this is not a driving force for the particular reaction in question. So if we now plug everything in to solve for our delta G, or part A, our delta G of the reaction will be equal to our delta H of the reaction, which was 140 kilojoules per mole, minus our temperature, which is 298 Kelvin, times our entropy, which would be a negative 0.039 kilojoules per mole Kelvin. So important thing to note there are units, namely the kilojoule and the kilojoule. Right, we want to make sure that when we're combining our ideas of delta S and delta H, that we're in terms of the same unit. Remember, delta H is usually kilojoules, while delta S is joules. So it doesn't matter which one you change, just so long as you change one of them so that we're in the similar style of unit, whether that be kilojoules or joules. In this particular case, I've chosen to change delta S from that negative 39 joules per mole Kelvin to a negative 0.039 kilojoules per mole Kelvin. And if we add that up, solve for our Gibbs free energy, we get a positive 152 kilojoules per mole. And that is part A. For part B, right? Since delta G is positive, that means that this reaction is not or non-spontaneous. For part C and part D, since both the delta H of the reaction which was that positive 140 kilojoules per mole, and the delta S of the reaction being that negative 0.039 kilojoules per mole Kelvin, that means that both delta H of reaction and delta S of reaction are not or non-driving forces. That means this reaction is not temperature dependent. And basically is always non-spontaneous. So that's an example of looking at Gibbs free energy equation to relate a reaction in terms totally of the system, so that we can predict whether it's spontaneous or not. And so in this case, our delta G turned out to be a positive value, a positive 152 kilojoules per mole. Just because it's positive just says that it's not spontaneous. It does not say whether it's temperature dependent or not. So now we have to look at delta H and delta S and look at their sign values to answer the question of whether it is a temperature-driven process. The fact that both our values of enthalpy, delta H, and our entropy, delta S, are unfavorable or not driving forces is why this reaction cannot happen. It will never be spontaneous. Look to a very similar example in the next lecture, bringing in, a subtle new element, but not too different to the process. And we'll reinforce this idea of spontaneity or non-spontaneity, as well as temperature dependence. Look for that next.